Okay, so the first question on weak acids, titrations, and buffers wants me to write an equation about how HCN reacts with water. It's a weak acid, so it's equilibrium with hydronium, and it's anion, cyanide. Questions about that? Okay. Part B, which is the stronger acid, lactic or hydrocyanic. Lactic has a pKa or a Ka of 1.38 times 10 to the negative 4th, and hydrocyanic acid has a Ka of 6.17 times 10 to the negative 10th. So it's lactic because it has a larger Ka. The larger the Ka, the more it dissociates. The more it dissociates, the more hydronium it produces. The more hydronium it produces, the lower the pH. The lower the pH, the stronger the acid. And then what is the chemical formula of the conjugate base of lactic acid? So lactic acid is C3H6O3. Conjugate bases have lost a hydrogen, and they have a negative, they're an anion. That's the lactate ion. Questions about number 1? Okay. All right, number 2, I won't lie. It's hard. It's difficult. Some parts are easier than others. But this is kind of one of those that it's like the whole entire unit in one question. So it starts out and it's telling you about 20 milliliters of lactic acid being titrated with strong base, sodium hydroxide. Calculate the pH of the contents of the Erlenmeyer flask at each of the following points during the titration. So initially, when you just have the weak acid sitting there, you have lactic acid in water. It's a weak acid. It's 0.1 molar. Remember, this X is insignificant. To find the pH of a weak acid, which is all it is in the beginning, you do Ka equals X squared over 0.1. The Ka was given in question 1, so you plug that in. You solve this for X, and then X is hydronium, so you take the negative log of X, and that will give you the pH. That's how you find the pH of a weak acid. And that's all it is before the titration starts. Questions? Okay. Once the titration has started, we're reacting a weak acid with a strong base. So it's just hydroxide. It's a strong base. We have a right-hand arrow. Proton donor, proton acceptor. Okay, so this time our moles, our molarity, our volumes don't match. So we're going to have to put moles in the ice table and then go back to molarity later. So Lactic acid, I have 0.1 molar, and it's 0.02 liters. So 0.002 moles. My sodium hydroxide is also 0.1 molar, but I only have 5 milliliters. So this is 0.0005 moles. And then 0, we don't include water. Minus x plus x it's a right hand arrow. How do I find x? Limiting reactant, right? One of them is going to run out. Which one? The hydroxide is going to run out. So this is 0.0005, which makes this 0.0015, and this 0.0005. At this point in the titration, before the equivalence point, I've produced a buffer, right? I have conjugate base or salt and acid. So to find the pH of a buffer, I just need to know the concentration of these two things. So I'm going to divide them by the total volume at this point, which is 20 plus 5, or 0.025 liters. .06 molar salt or acid, sorry, and this is also 0.025. .02 molar. So my pH equals the pKa plus the log of salt over acid. And the pKa is the negative log of the Ka that was from the problem before. So that's a buffer. If you're doing a titration with a weak acid and a strong base, you produce a buffer before the equivalence point. Up to the equivalence point, it's a buffer. Okay, part C, same reaction. But this time, I always have the same amount of acid to start with. But now I've added 20 milliliters of base. Minus x plus x. What's my limiting reactant? You don't have one. That's the point of the equivalence point. They're equal. So I've run out of both. And now all I have is moles of salt or weak base divided by total volume, which is 0.4 liters. .05 molar. Weak base in water. How am I going to find the pH if I don't have any hydronium or hydroxide? It's not, because I've added a strong base to a weak acid. This is the trickiest part. When you're here at the equivalence point and you have this in water, you have to start again. I know you love that. You have an equilibrium situation where now water is the acid, proton donor, and you make hydroxide. At the equivalence point, you have a slightly basic solution. You've added more base, same amount of base, but it's a stronger base. Ice table. This is 0.05 molar. Again, X is so small that it doesn't matter. It's very small. This is the calculating the pH of a weak base. To calculate the pH of a weak base, kind of like a weak acid, you do Kb equals X squared over 0.05 molar. You solve for X, you can get the pOH. Once you know the pOH, can you find the pH? Yep, 14 minus. What about Kb? I was given Ka. I wasn't given Kb. What do I do? Quit? Give up? Yep.
Well, you have to find the pOH and then find the Kb from that.
I can't find pOH without Kb. I need this number to solve for X. But I have Ka. Do you know how they're related? Now you do. Kw equals Ka times Kb. Solve for Kb. Plug it in here. Solve for X. Find the pOH. Find the pOH. Get the pH. This is really fun. Part C, lots and lots of work. Terre Haute South High School is calling me. Hello. I was afraid it was an emergency from the office, but okay. Questions about this? So, use K, W and Ka to find Kb. Use Kb to find hydroxide. Use hydroxide to find pOH. Use pOH to find pH. And then cry. Or sleep, take a nap. Yeah. Okay. The next part is when you've added half the volume that it took to get to the equivalence point. Good news. At the half equivalence point, the pH equals the pKa. Just take the negative log of the Ka. We could do the math to prove that. I don't want to. Questions? And this is always true. Use that to your advantage. Yes?
Did you say that the pH would be the negative log of the Ka?
The negative log of the Ka, which is the pKa. Yep. And then at part E, when you've gone past the equivalence point, you have an excess of hydroxide. So you would do this exact same thing here, but instead of your limiting reactant being the hydroxide, your limiting reactant would be this. You would wind up with some excess hydroxide. Find the concentration, find the pOH, find the pH. At that point, you've overcome the solution with hydroxide. You've made a very basic solution, and it's just the hydroxide is winning at that point. You've neutralized it, and then you've added some hydroxide, and you just have a base. Questions? Okay, so obviously, you wouldn't have time to do all of this on a test, unless this was your only FRQ. But be ready for any one of these parts of a titration to show up as an FRQ, and you have to know how to deal with it. Before you start, before the half equivalence point, or between, at the equivalence point, half equivalence point, or after the equivalence point. Any one of these could show up as an FRQ, and you would have to know how to deal with it. Okay? These are just kind of explanation questions. Any questions about 3, 4, or 5? Okay. Go to acids and bases summary, please. Okay, so this one, strong acid. So if this is 0.2 molar, this is 0.2 molar. Just take the negative log of 0.2 to find the pH. Right? Strong acid. Strong base. Water is a spectator here. If this is 0.01 molar, this is 0.01 molar. Find the pOH, which is 2. So your pH is 12. Yep.
Will we have to know like what's a strong base, what's a strong acid?
Yes. So the strong acids just memorize. Nitric, well, there's a list. Look at the list. And then any hydroxide is a strong base. The only weak base is NH3. Otherwise, they'll explain it to you. They'll tell you. Part C, benzoic acid is a weak acid. They don't tell you the formula, so I'm just going to write it like this. HA, doesn't matter, plus water, equilibrium. Oh, they tell you that the pKa is 4.2, which is going to help you, but 0.1 molar use the pKa to find the Ka, find X, take the negative log. This one is Henderson-Hasselbalch. Salt and the pKa is 4.90. Yep.
For one C, do we really have to do an acid, or do we just do the concentration of hydroxide squared over the acid? Wouldn't you equivalence it from that?
Yes. That's fine. I mean, if you know that, I was just showing where it comes from. Yep.
Thank you.
Questions? Okay. Number 3, a 0.1 molar solution of a weak acid has a pH of 2.80. Calculate Ka and pKa. This is working backwards. So Ka equals hydronium squared over acid. To get hydronium, we're going to have to take (10 to the negative pH, plug that in here, plug in 0.1 molar, and solve for Ka. That one's just a little trickier because they give you pH instead of hydronium. Okay? Number 4 is a titration. You have the pH of the solution at the half equivalence point is like 9. Or at the equivalence point, sorry, is 9. So phenolphthalein is a good indicator. Is the acid strong or weak? My pH does not wind up at 7. So I started with this and I ended up here at the equivalence point. It must have been a weak acid.
How do we know what a good indicator is?
There's a table of indicators and the pH at which they change color. So you want your indicator to change color at that pH. So it would just where it falls in line.
Do we have to memorize that? Or?
Yes, I think on the AP test they usually give you the table.
Okay.
You just have to know how to read the table. What volume of acid is needed to neutralize all of the sodium hydroxide? 20, 21, 22, whatever. And then write an equation and find the molarity. So it's weak acid plus sodium hydroxide makes A minus Na, I guess, A, and water. This, they told you, was 25 milliliters and 0.1 molar. And then it's a 1-to-1 ratio. So I can find moles of acid using that. 25 times 0.1 divided by 1,000. 0.0025 moles of acid divided by the liters of acid, which was 20 milliliters. This is stoichiometry, stuff that we've known for a long time. 0.125 molar. Don't lose this point because you're stressed out about not knowing acids and bases. This is just stoichiometry. Milliliters to moles, moles to moles, back to molarity again. Okay, the last one. The ionic product, oh, maybe not the last one. The ionic product of water at 298 Kelvin is 1 times 10 to the negative 14th. At 50 degrees Celsius, or 323 Kelvin, it's 5.47 times 10 to the negative 14th. Calculate the pH of water at this temperature. So, Kw is hydronium times hydroxide. And no matter what temperature you're at, these are still equal for water. So 5.47 times 10 to the negative 14th equals, we'll just say x squared. If I find x, I have hydronium. So take the square root. And I can take the negative log of that to find the pH of water at that temperature. Does that mean that at 50 degrees Celsius, water is an acid? Has a pH of 6.63. Does that make it an acid? Does that mean that if I got water up to 99 degrees Celsius, it would be really acidic? No. It means that at different temperatures, my pH scale shifts. That pH scale saying 7 is neutral, that's only true at room temperature. At higher temperatures, this is neutral. And less than that is acid, and higher than that is base. So the pH scale just shifts a little bit at different temperatures. Water is always neutral, no matter what temperature. Just the pH scale is different. Okay? And then, if increasing the temperature shifts my reaction to the right, that must mean that this is an endothermic reaction. Right? Energy must be a reactant. So this reaction the dissociation of water is endothermic because increasing the temperature shifted it to the right, produced more hydronium. Questions about this one? This one's pretty simple.